Okay, let's go ahead and start the class. It's the perfect weather today to canceling the class, right? No, I don't want to be here, and I know you don't want to be here as well. So let's get this over with as soon as possible. Then we can get out to the wild. Okay. So we talked about the Reynolds transport theorem. We talked about the conservation of mass. And I'm just going to rewrite the Reynolds transport theorem. And the changes of extensive property in a system is equals to, over time, is equals to rate of change of the intensive property over the control volume plus the net rate of inflow or outflow of that intensive property over the surfaces of that control volume or the control surface. So this was the Reynolds transport theorem, okay? And we use this to find the conservation of mass equation. Today, when we solve a couple of examples, we will solve more examples when we are done with this chapter from the conservation of mass. But next step is to find the other governing equations that are very important in fluid flow. The next one that we are going to work on is the momentum equation. Or to be a little more exact, it is the linear momentum equation. Okay. And this is derived based on Newton's second law. Sigma F is equals to the changes in linear momentum over time. Okay, what does the second law tell us? Sigma F is equals to d mv dt, right? That's the changes in linear momentum with respect to time. The more common form of the second law is ma, right? This is assuming m is constant, so this comes out of the derivative, and the total derivative of velocity with respect to time is acceleration. So don't be confused. It's essentially the same thing. We are not just making any assumptions. So linear momentum and the sum of all forces. Since force is a vector, this tells us that we are dealing with three equations in each axis. We have an x momentum, y momentum, if you're dealing with Cartesian coordinate system, of course, and z momentum. If you are dealing with circular, cylindrical, or spherical coordinate systems, we will still have three components, but that will be a little more complicated. Okay, so let's apply the Reynolds transport theorem to linear momentum. Extensive property here is linear momentum, which means that your intensive property, which is linear momentum divided by m, is just velocity. Okay? And we are actually here, we are assuming density in mv in calculating the linear momentum. We are assuming density is uniform everywhere. So uniform or constant density everywhere. Uniform rho. If you don't make this assumption, your m is going to be equal to the integral of rho over your volume. So instead of rho multiplied by total volume, since density is changing over the volume, we want to take the integral of density with respect to volume, right? Is this clear? Yeah. Which essentially means that your linear momentum is going to be integral of rho v velocity over the volume, right, instead of mv. So this is the linear momentum we are going to use, the extensive property B we are going to use in the Reynolds transport equation. So d rho v dv divided by t, this is for the system. So changes of the linear momentum of a system is equals to rate of change of linear momentum inside the control volume plus the influx or outflux of linear momentum out of the surfaces. So the only thing we did here, as long as you know the Reynolds transfer theorem, the only thing you really do here is just you plug in these values, this for your extensive property, linear momentum, and you plug in v, velocity, for your intensive property, right? And this will give you the momentum equation. But on one hand, on the other hand, we know this, the changes of linear momentum of a system with respect to time is equals to sigma f. So I'm going to substitute, I'm going to replace this with sigma f. And we can have the momentum equation in terms of a control volume. Okay. So net forces or net forces in your system is going to be equal to the rate of change of velocity or linear momentum in a control volume plus the rate of inflow or outflow of the linear momentum out of or inside into the control volume. This is the general form of the momentum equation. And using the integral method. We are going to use the differential method later in 2 weeks or so to get to the same equation just using the differential methodology. So let's see how we can simplify this equation and solve at least one example. And I assume you brought your copy of the examples we are going to solve for this chapter. If not, we have some extra ones here. You can come pick it up. And it is also uploaded on Blackboard, so you can go there and check it out. This is example 5.10. This is, it says, as shown in the figure E510A, a horizontal jet of water exits a nozzle with a uniform speed of V1 equals to 10 feet per second. Okay. It strikes a vein and is turned through an angle theta. Turn angle theta. A similar situation is also known as in this video, whatever. Determine the anchoring force needed to hold the vein stationary if gravity and viscous effects are negligible. So viscous effects, we are going to neglect it. Gravitational forces are also neglected. We want to find the anchoring force. So we are told to find a force. What is the equation we have that will help us find the force based on velocity, right, or linear momentum? the momentum equation. Let's actually have the figure. This is your vein. Flow is coming in like this from a nozzle, and then it's changing direction. And the turn angle is theta. V1 is equals to 10 feet per second. A1 is equals to 0.0 feet squared. Okay, and this is 0.2, this is 0.1. You're required to find the force. So let's see what we can do with this equation. The first thing is we are not told whether this is a steady state or a transient condition, but since we don't have any time dependence, we haven't talked about time dependence at all. We can assume that it is a steady state condition, so this part goes to 0. And there is only one force that is applicable here, and that is the anchoring force. It's probably a little inclined, right? So we can have two components of this force. Let's say this is your z direction. This is your x direction. So Fa, anchoring force, will have two components, Fax, Faz. Okay? Since we have forces in two different directions, we have to write two momentum equations. Right? The idea was, again, force is a vector, velocity is a vector. So we need to have, we have three different momentum equations in three directions, right? Each direction has its own momentum equation. Okay. So sigma f in the x direction is equals to, that the first term is 0, so partial t is 0, integral of cs v rho dn dA. We can write the same equation for the z direction. But the only force in each direction is F and Z, so sigma F, it will be just 1F. Integral of V rho Vn dA. Is there any questions so far? Okay. So velocity itself has two components, right? One component in the Z direction, one component in the X direction. The component in the X direction is going to be called U. Component in the Z direction, we are going to call it W. Okay. V1, based on what you can see in this picture, in this figure, is only in the x direction. So 10 feet per second I, right? And 0 k. While V2 is an inclined direction. It has some incline to it. So we have to find the projection of V2 in each direction. What is the projection of V2 on the x-axis? It's V2 cosine of the angle, right? This angle. V2 cosine of I. And the projection of V2 on this axis is going to be V2 sine of this angle, right? Okay. Is there any questions so far? Okay. Let's continue. So let's try to solve the problem in the x direction first. f(ax) is equals to this integral, right? In the x direction. Flow is going in the x direction, and whatever that is going out in the x direction, right? The linear momentum in those directions. We're going to assume density is constant, so we can take it out of the integral. We are also told that the velocity is just 10 feet per second, so it's uniform. It's uniformly distributed. We can take that out of the integral as well, right? So we're going to have v1 in the x direction, f(ax), v1, rho, v normal to the surface, integral of dA, which is area, right? That's for the part that is coming in to the control volume, minus v2. That's the velocity in the x direction. Okay? So that's v2 cosine of theta this time. And it's not a vector anymore because we are dealing with the rho What should we do about this part? What is the velocity n? That's velocity normal to the control surface, right? So it's not velocity in the x direction. It's the velocity, the second velocity. That's the velocity normal to the control surface, which is only v2, not the projection of v2 on the x direction, right? So that's something that you have to keep in mind. So this is going to be only v2, and velocity normal to the surface in the x direction is also v1. Okay, so f(ax) is going to be, these two are equal, rho v1 squared a minus rho v2 squared a cosine of theta. Okay, this actually, the negative sign, it should be negative this, positive this. M out minus M in. Just make sure you are clear on this one. Two surfaces, we have to take this integral on two surfaces, and we should find. This is how you calculate the anchoring force in the x direction. Okay. Well, how can we don't have a number here right yet, right? Because we don't have v2. And do we have theta? Let's see. We don't have theta, but we can. This will go away later. We have the area, that's 0.06, and it's not going to change here as well. We have the v1, 10 feet per second. What can we say about v2 based on the information given to us? Go back to the conservation of mass. What did the conservation of mass tell us? It's a steady state. You don't need to rewrite the whole equation. It's a steady state equation, right? Density is constant. So whatever is going in is also going out, right? Which means that m dot in is equals to m dot out. Rho AV in is equals to rho AV out. Rhos are equal. So A in V in is equals to A out V out, or A1 V1 is equals to A2 V2, right? Right? Area is also the same, which means that the magnitude of V2 is equals to the magnitude of V1. Their direction is different, but the magnitude is going to stay the same, right? Does this make sense? Based on conservation of mass. Okay. So we can simplify this even further and replace this V2 with V1. And I'm going to take V1 out. You get 1 plus cosine of theta. That's the anchoring force in the x direction. There's a negative sign. That's -1. Right. Cosine of theta -1. Okay, let's do the z direction now. In the z direction, the only force we have is FAZ, right? And then we have to take this integral over two surfaces, right? Surface 1, surface 2, right? What is the velocity in the z direction on surface 1? Velocity in the z direction on surface 1. 0, right? So on surface 1, if you want to say, let's actually write the two integrals. So integral of v rho vn dA on surface 1, negative sign, plus the integral of surface 2, v rho vn dA. Okay. This is 0 because flow is not moving in the z direction on surface 1. What is the velocity in the z direction on surface 2? v2 sine of theta. Since v2 was equals to v1, you can say v1 sine of theta. And velocity is uniform, density is uniform. This velocity is also uniform. You can take all of them out of integral, and integral of dA is going to be a. So this part is 0. So F anchoring force in the z direction is equals to rho v1 squared a sine of theta. Okay. Cosine of theta -1. So we have the solution. How can we find the total anchoring force? Since your inclination is by theta degrees, we can actually don't need to know the inclination. That is going to be a square root of FAX squared plus FAZ squared. Right? What is FAX squared? This squared. And I'm going to just write it after all of the simplification. You can take rho v1 squared a out of the square root, and 1 minus cosine of theta squared plus sine of theta, sine squared of theta, right? That will be it. And we are not going to go any further with the simplification, so we're going to stop here. If we had the theta, we could have calculated the forces easier. It would have been much easier. Is there any questions? Okay. So, there was one thing that I think I forgot. We didn't have enough time, to cover in the previous lecture, and that was the conservation of mass for a deforming contour volume. Let me talk about those a little bit, then we'll move on. So we want to go back to the conservation of mass for a second, and then We'll continue the discussion here. The last thing we talked, yes. Yes. The last thing we talked about when it came to conservation of mass was the moving control volume, right? The moving non-deforming control volume. But then the question is, what if your control volume is deforming? An example of it is the movement of a syringe. Your control volume is moving out of the syringe, right? So this is actually a very common phenomenon. How should we deal with this? Again, the conservation of mass equation was that mass of the system divided by time is equals to changes of mass in the control volume, rho dV, CV, right? Plus CS, rho W, V, and since the control volume is moving, we use, if you recall from the previous lecture, we said velocity of the fluid is going to be equal to W plus W of velocity of the control volume. And this is the velocity we are going to use in this equation. But here the difference between this and the last thing we discussed in the previous lecture is that the control volume itself is deforming. It's not just moving, but it is also deforming. How should we deal with this? The only difference here is the fact that this part won't be 0 anymore, right? Because rho dV is changing, that's for sure. So you always have the presence of this part. And also, this normal vector may change, right? Think about it this way. Let's say this is your control volume. These are walls. So inflow, outflow. What is the normal vector in this direction? It's this, right? And the normal vector in this direction is this, right? If your control volume is deforming, let's say your new control volume looks like this, then the normal vector has changed, right? So this is something you have to keep in mind. So eventually, what this means is that if you are dealing with this type of problems, you probably have to take the integrals. You probably won't be able to simplify this, except for a specific condition. We will solve an example about on the syringe that is also included in the examples I've printed out for you, but not today, in a later day. That doesn't require taking the integral. But in most cases, if your control volume is deforming, you have to take the integral. And it's a very complex situation. That's why you have to, I mean, you never see these type of problems in a class. And if you want to solve this type of problems, you have to use computers, computational fluid dynamics, or CFD, which you probably have heard about, hopefully. OK. So moving, deforming control volume, conservation of mass. This is something that was left over from the previous lecture. Well, what if your control volume is moving and we want to find the momentum equation for a moving control volume? This essentially is going to be the same analysis as the moving control volume, conservation of mass for a moving control volume, right? And you will eventually end up with this sigma f is going to be equal to changes of linear momentum inside the control volume plus, and here's the difference, your velocity in that specific direction, W instead of V. And where W can be calculated using this equation. So moving control volume, conservation of the momentum equation. If the only thing that is moving is your control volume, your W is essentially equals to the velocity of the control volume, right? And if you're dealing with a steady state, the first part goes to 0. And I mean, you can simplify this. So in that case, sigma F will be only that this is control surface. W rho WdA. I mean, as you can see here, these equations in their most general form are very complex. But when you're dealing with a specific problem, you can usually simplify them and make them create simpler problems with them, right? So don't be scared from the equations. Just learn them, put them on your equation sheets, whatever. You don't need to memorize anything. And as long as you understand the Reynolds transfer theorem, you can drive all of these equations on your own, right? And learn how to simplify that to fit your specific problem, okay? And let's actually, we are not going to solve an example from this part today, but we will solve an example from this part in the next lecture. In the next lecture, we will only solve examples. I will also print out another set of problems for you to solve in the next lecture. Okay. So one other equation we want to deal with is the moment of the momentum equation. Sometimes forces and linear momentum are not the thing you are looking for. Sometimes torques are the thing that you are looking for. How do we calculate the torque? It's the cross product of your arm, called R, by F, right? Okay. Which means that for your Reynolds transport theorem, you want to take the cross product of d dt integral of rho dv, rho v dv. That was for the system. And that has to be equals to R sigma F, right? If you play with this a little bit, eventually you come to the conclusion that you can take R2 inside the integral and do R which this tells you that R cross V is your extensive property. So we can apply the Reynolds transfer theorem to this. Okay. Let me ask you this. What does R cross V remind you of? What is that property? Have you ever seen this before? For people who have passed dynamics, we have some people who have passed dynamics, right? For people who have passed dynamics, what is R cross V or R cross R dot? Does that ring a bell? Okay. This is actually a property called angular momentum. So we have linear momentum, mv, and a specific angular moment. And if we usually use h for it. H So you haven't had H, you haven't dealt with H in your dynamics? No? Okay. H is equals to mvr r cross mv. It's called the angular momentum. So moment, taking the moment of the momentum equation is going to give us the angular momentum equation, right? So extensive property is going to be the angular momentum, which we have the, if I change this to B and include the B here, this is the Reynolds transport theorem. Our B here is M V R cross MV, right? That's capital B. What would be the intensive property? Intensive property will simply be R cross V, a specific angular momentum, or a small h. So we can say the d dt of this is the same as R and V, R cross MV. The only thing is we are not assuming density is uniform, right? So we can write the Reynolds transport theorem for this. Changes inside the changes of a specific angular momentum inside your control volume plus the flux of your angular momentum in or out of your control surfaces. So we have had 3 equations so far: conservation of mass, momentum equation, and angular momentum equation. If you are, I assume no one here is getting a bachelor's in aerospace engineering, but if you were taking a bachelor's in aerospace engineering, this equation is actually a very important equation in orbital mechanics. And you will see that pop up a lot. Okay, let's talk about the last equation we wanna see, and then we'll solve some examples. And that will be it for this chapter, hopefully. The last equation we want to deal with is the energy equation. Okay. So energy equation, we want to use the Reynolds transport theorem again, this theory, to find the energy equation. But before finding the energy equation, we want to talk about first law of thermodynamics again. Who can tell me what the first law was? Is there anyone who remembers what the first law was? First law of thermodynamics. E equals to, or delta E is equals to, doesn't ring a bell? First law of thermodynamics. No? The rate of change of energy stored in a system is related to heat input and work done on the system, right? So what was the equation for it? Seriously, no one remembers? That's all right. So energy of the system is equals to Q, or changes in energy of the system is equals to changes in the heat input or heat into of the system minus the work done by the system. That was the idea. Or net rate of energy, net rate of increase of the total stored energy of the system is equal to the sum of net time rate of energy addition by heat transfer into the system and net time rate of energy addition by work transfer into the system. So what does this tell us? This part is talking about d of the total energy dt, right? How did we calculate total energy? We are not going to assume density is constant, so your m is going to be integral of rho dA, and then we can add an e in between. So this is for the system. Is going to be equal to sigma q in minus q out of the system plus this q dot w dot in of the system. Okay. This part we can rewrite using the Reynolds transfer theorem, right? Which converts whatever that is happening inside the system to whatever that is happening inside the control volume. It is going to be easier for us to deal with. So just going to rewrite this here, partial t over the control volume of rho e dv plus whatever happening over the surface, rho e velocity normal to those surfaces is equals to the right-hand side of this equation. This will be the general form of energy equation for you. But we already know from thermodynamics that energy stored in the system itself is a combination of internal energy U and the kinetic energy V2, V squared over 2, plus the potential energy Gz. So we can replace all of the E's here with U V2 squared plus Gz. Okay, this is the most general form of the energy equation. Okay, energy equation in general is very much out of the scope of our course, right? We have seen some implications of it, but you will mostly deal with this equation in your heat transfer class, right? A different form of this equation, but it's the same energy equation nonetheless. So I would say make sure you understand the equation before moving on, because in the heat transfer, you're going to have a hard time if you don't. I mean, it is going to be harder to understand energy equation in heat transfer if you don't understand it here. I don't mean you're going to have a hard time in heat transfer, but it is a hard course. Okay. So we are not going to jump further into the energy equation here. And most people don't even mention energy equation in a fluid mechanics class. Well, here it is for you. You can see the energy equation is in all of its glory. And that will be it for the material of chapter 5, right? We have actually, in my notes that is posted on Blackboard, you can see more detail on the energy equation, and eventually you will get to an extended form of Bernoulli's equation that includes the work done on the system and energy into the system, heat into the system as well, but we're not going to go over it. And we are going to solve a couple of examples. Let's see, just make sure. Yep. Okay. Is there any questions so far? How do you feel about the material of this chapter? Is it too complicated? Is it not complicated at all? Somewhat in between? Okay, so, okay, somewhere in between. That's all right. Okay, so what we're going to do is we are going to solve another example, one more example. I mean, if you have enough time, we're going to solve 2 more examples. And then I'm thinking I will, if I can, I will post an online video. A video will be posted online anyway. So I will post a video on YouTube, right, in which I will solve some example problems, right? I didn't think I could finish this today, so that's good. And then on Tuesday, we will start chapter 7, which is dimensional analysis. We are a little bit behind, right? So we want to catch up. So I will post whatever example I want to solve in the next lecture for you on YouTube. You don't have to watch it, but you're also welcome to watch it if you want to. And then you can talk to me. You can ask questions if you had any. Whenever we were done with chapter 7 and chapter 8, we will spend like 1 or 2 lectures on solving more example problems and like addressing your questions or issues, right? So, and you can always come to my office, send me an email or whatever. And people who come to my office or send me emails, you know that I will get back to you eventually. I try to help you through email or Teams or whatever, right? So, yeah. And if there's no other questions, let's solve this example. This is example 5.11. And it tells us, as shown in the figure 5.11, water flows through a nozzle attached to the end of a laboratory sink faucet with a flow rate of 0.6 liters per second. So 0.6 liters per second, that's your flow rate. And it has a very weird shape. This is your nozzle. And your control volume is also drawn for you. This is going to be your control volume. This is going to be the inlet of the control volume. This is going to be the outlet of the control volume. So we don't care about what is happening here, right? As long as we are given the velocity. The nozzle inlet and exit diameters are 16 millimeters and 5 millimeters. So 16 millimeter here, 5 millimeter here, respectively. The nozzle axis is vertical. The mass of the nozzle is 0.1 kilograms. Mass of the nozzle itself, we're going to call it Mn, 0.1 kilograms. And the pressure at section 1, pressure here, so P1. P1 is 464 kilopascals. We want to determine the anchoring force required to hold the nozzle in place. And we are also given some more information that this is 30 millimeters. This length is 30 millimeters. And what else? Okay. Again, we want to find the anchoring force, F of A. That's equals to that's the question we need to answer. So let's just draw your control volume. Just the control volume, right? We have an inlet here with a uniform. I mean, we are not told whether it's uniform or not, but the outlet with W2, we are told is uniform. Let's see if it's, I mean, this is also uniform. So velocity is coming in. What are the forces that are present here? One is the anchoring force in this direction. One is the weight of the nozzle that is pushing the nozzle down. And we also have the weight of water inside the nozzle. These are the forces. We also have the pressure forces, right? Pressure, we have P2 here, and we have P1 here. How can we calculate pressure force? Pressure is force per unit area. So to find the force applied by pressure, you just have to multiply it by area. So F of P1 is P1 multiplied by whatever the area of 1 is. Fp2 is P2 multiplied by whatever the area 2 is. Sigma F, if we assume that this direction is positive z, sigma F is going to be equal to sigma F in the z direction is going to be equal to F of A plus P2A, P2A2 minus P1A1 minus W. That's the weight. This is the weight force, not the velocity. Weight of nozzle and weight of water, right? These are the only forces that are present here. And this is equals to the other side of the momentum equation. It's a steady problem. Let me actually write the momentum equation and then. It is a steady problem. So on the right-hand side, you're going to get, let me just write it completely, CV rho v dv, right? By a steady. So this part is 0. And then integral of v rho vn dA. The thing is, we only have flow in one direction, right? So we only have one momentum equation and two surfaces, one inlet, one outlet, right? Okay. We can simplify the equation. Velocity is distributed uniformly. Density is also not changing. And velocity, since there is no inclination, there is no change, there is no turn, v dot n is always, v is always perpendicular to velocity. So this integral will become rho v squared integral of dA, right? Or rho v squared a on two surfaces. One, rho v squared in, or rho v squared out, minus rho v squared a in, right? So sigma f here is equals to rho v squared out minus rho v squared in. Is this clear? Okay. Let me actually. So your anchoring force, and we're going to move all of the other forces to the other side, is going to be equal to rho v squared out minus rho v squared a in minus P2A2 minus P plus P1A1 plus nozzle weight plus the water weight. How do we calculate the nozzle weight here? We are given the mass of the nozzle. That's 0.1 kilograms, right? How do we calculate the weight of the nozzle? That's 0.1 multiplied by the gravitational acceleration, so mg, right? 0.1 multiplied by 9.81. So this will be 0.981. newtons. Okay. What about the weight force of the water? How can we calculate the weight force of the water? That's gamma multiplied by the volume, right? For fluids, that's how we calculate the weight force. Gamma multiplied by the volume. So, or rho g multiplied by the volume. So rho volume g. Let's see, what else? Oh. Are we given the areas? We are given the diameters, right? 60 millimeters and 60 millimeters and 5 millimeters, which means that we can calculate the areas, and based on that, we can also calculate the volume. Okay. And pressures are given to us. Everything else is given to us. We can just plug them in and find the final anchoring force, which is going to be equal to 77.8 newtons. Okay. I'm not going to go over the derivations. Is there any questions? Is this all clear? That's good. So, moving on. Let's solve another example. This other example, that's example 5.13. That tells us air flows steadily between two cross-sections in a long, straight portion of a 4-inch inside diameter pipe, as indicated in the figure. So this is the pipe. We have a control volume inside. A 4-inch portion of this pipe is part of this control volume. Okay. And so where the uniformly distributed temperature and pressure at each cross-section are given. Pressure and temperature are uniform. P1, this is 0.1, cross-section 1. Cross-section 2, P1 is 100 psi, and T1 is 540 Rankins. P2 is 18.4 psia. T2 is 453 degrees Rankine. Okay. We have the average air velocity at section 2, which is 1,000 feet per second. V bar 2 is 1,000 feet per second. Again, we are given the average air velocity. What does this mean? It means that we can safely assume that velocity is distributed uniformly, and the magnitude of that velocity is the average velocity, right? And we find an example, average air velocity here at 0.1. We actually have solved this example before for the conservation of mass. Is 219 feet per second. We want to assume uniform velocity distribution at sections 1 and 2. We want to determine the frictional force exerted by the pipe on the wall on the airflow between exerted by the airflow, I think, between sections 1 and 2. So what are the forces that are present here? One is the friction force opposite to the flow direction. The flow is going in this direction. Friction force is going to be in the opposite direction. This is something that you had on the exam as well, right? We call the shear stress was negative, whatever, which means that it is in the opposite direction of the flow, right? Flow is going in this direction, friction force or the shearing force, whatever, is going to be in the opposite direction. And then we have the pressure force on this section 2, cross section 2, P2A2, pressure force P1A1. Okay. And something, if you were confused on how to find the direction of the pressure force, it is always opposite to the normal of the surface. Normal of the surface always points outward. Pressure force always points inward on the surface, right? Same is true here. Normal is in this direction. Pressure force in this is in this direction, right? That's how always you determine the pressure force. So pressure force direction, pressure force direction, normal to the surface, that cross section, whatever that is, normal to surface, inward, in the inward direction. Okay, that's in the opposite direction of the normal vector. Okay, so we have all of the forces. Sigma F is going to be equal to, and we are going to assume that the positive x is this direction. So sigma F is equals to P1 A1 minus R minus P2 A2. And then that is equals to this, right? It's a steady state solution. So the first part is 0, as most cases have been in our analysis. And then we need to get to this part. We are told to use the average velocity, which is uniform, doesn't change on the cross section, right? We can take it out of the integral. The same is true for density. So for both surfaces, we are going to end up with rho v squared a, right? That was the idea. If your density doesn't change, if your velocity is uniform, you don't need to take the integral. You can take all of it out of the integral. Something to keep in mind is that this part always refers to the velocity that is normal to your surface area. This part always refers to the velocity in the direction of the force. In this problem, they are all the same, but in the problem with the turn angle, they weren't the same, right? So that's something that you need to keep in mind. Okay, so we are going to have rho 1 v1, that's rho 2 v2 v squared 2a2, which is out, whatever out, a linear momentum out, rho 1 v1 squared a1. Okay? We can actually, you may actually see another form of this in the book, if you were to read the book. It is essentially the same thing, just a different representation. We already know that rho VA is equals to m dot, mass flow rate. So your book also does m dot 2 v2, m dot 1 v1, right? So if you, instead of rho v squared a, you saw m dot v, they are the same thing. Okay? So do we have the velocities? Yes, these are the average velocities. Keep that in mind. We are dealing with average velocities. If we were not dealing with average velocities, we couldn't assume that the velocity is uniform on these surfaces, and we couldn't simplify that integral. Okay. We have the average velocities, right? 1,219. We have the areas. Areas are the same. I think we are given the pipe's radius. Areas are the same. I think we were given the pipe radius in the previous example 5.2 we solved in the previous lecture. We can calculate the area from that information. We also have the density. We are given the pressures. We calculate, if you recall, we calculated the density in the previous lecture. So you have it there as well. We are given the pressures. We also have the areas. It's the same, which means that we can calculate the reaction force. And if you plug in the numbers, you will end up with 53, or the friction force, 53 foot-pounds per pound mass degrees Rankine. Do we have any questions here? Okay, let's solve one more example, and then I will let you go. Actually, rewrite these parts. Partial T integral rho v sigma. This is example 5.14. We are given the flow example of 5.4, which I think we solved to be vertically upward. Let me, we solved 5.4 as well. It should be, yes, we did. This is the one in which we had to take the integral. And we want to develop an expression for the fluid pressure drop that occurs between sections 1 and 2. So we have a vertical flow. Flow comes in with a uniform distribution W1, and then goes out with a non-uniform distribution. So velocity distribution at cross-section 2 is non-uniform. Okay? I'm going to find an expression for the fluid pressure drop. It is a steady condition. So, and this is the momentum equation. This part goes to 0 again. Goes to 0 again. And we are going to left off with sigma f is equals to integral of CS V rho Vn dA. Okay. In this problem, velocity is always normal to the surface. So these two velocities are the same, right? Always normal to the surface, always in the z direction. So both of them are in the same direction, v dot n and v, right? V dot n has to be normal to the surface, and velocity has to be in the z direction. V in the z direction. I just want to make sure you understand this. This has to be in the direction of the force, which is the z direction, right? This has to be normal to your cross section, normal to 1 or 2, right? If the pipe was something like this, then this would have been v dot n, but this v would have been the velocity in this direction. They would have been different, right? But in this problem, they are both in the same direction, so they are both the same. Okay. So sigma f in the z direction is because, again, we want to find the pressure drop, right? So we have to calculate the net pressure force and include all of the other forces, and from there calculate the pressure drop inside this pipe. So sigma f The inlet area here, we have uniform velocity. We can take it out of the integral. Density is also constant. Take it out of the integral. So for the in part, we are going to have in part always has negative. Rho v a in plus. This time, velocity is not uniform. These two are in the same direction, but they are not uniform. So we're going to get W. This is W2. Velocity in the z direction. We're going to call it W. W dA. And this is W2. The dot product of two vector is the magnitude of a vector by itself is a magnitude of vector squared. So we can replace it by rho W2 squared. Okay, let's talk about the sigma of forces. What are the forces that are present here? We are not told to neglect friction or gravitational force. So friction force is present, and also the gravitational force. Okay. Friction force opposite to the flow. Gravitational force or weight also opposite to the flow in this case. Pressure force normal to the surface in the inward direction. So we're going to have for sigma f, we have P1A minus P2A. A is the same for both cases. So we're going to keep it as A minus W. This will be the sigma F. We should be given the reaction force here to be able to find the pressure drop, because we are not given pressures and we are not given the reaction force. But the thing that I want to work on, that I want to focus on, is that integral. That integral, the distribution, the velocity distribution, W2 is equals to 2 W1, 1 minus R divided by R squared, right? If you recall, we had this distribution in the previous lecture as well. So if you want to take that integral, you have to take the integral of rho W2 squared, which means that we are going to deal with 4 W1 squared, 1 minus R divided by R squared, squared dA. What was dA? That this was dA of a cylinder. So dA of a circle, d of pi r squared, or 2 pi r dr. Okay? So I'm going to replace this with 2 pi r dr. And then this integral is not very, it is not a very complex integral to deal with, it's just a polynomial integral. But I just have to be careful. We can take rho 4 and W1 out of the integral. Integral of, then we can expand this. It will be 1 minus 2 r divided by r squared plus r divided by r to the power 4 multiplied by an r. We can also take the 2 pi out. Let me take this out. Multiplied by an r. So r third to r squared, and r fifth to r fourth dr, right? Can we take the integral here? Yes, we can. And then r changes from 0 to r. So we have 8 pi rho W1 squared r squared over 2 minus, this integral is going to be 2r fourth to 4r squared plus r sixth to 6r fourth from 0 to r. If you put in 0, this will become 0. If you put in r, you're going to have r squared divided by 2 minus 2r to the fourth. So let me actually put it. R squared divided by 2 minus 2r fourth to 4r2 plus r6 to 6r4. So this will be r squared divided by 2. These two will cancel out, and you will end up with the solution to this integral will be 8 pi rho w1 squared multiplied by r squared, that's the radius of the pi, divided by 6. You plug that in here. And then as long as you have the friction force, or you're told to neglect the friction, you can find the pressure drop. Pressure drop is P1 minus P2, right? Just have to make sure to take the A out, take it to the other side, and you'll be done. Is there any questions? How do you feel about this last question? Where's the confusion? If you feel so about it, where's the confusion? Or just need more time to think about it? More time. Okay. Yeah. So I guess that's it for today. Have a good weekend. And see you on Tuesday. I will post a lecture with the solutions to the example problems. And pardon me? Tomorrow. Today or tomorrow. Whenever your homework comes out, you will have 1 week to submit the answers. Is it? Yes. Okay, I didn't know that. Thank you for bringing this up. So next Tuesday is a wellness holiday. We won't have any class on next Tuesday, but I will try to upload that example problem session online. It is not part of the lecture. You don't have to watch it. You're welcome to watch it to learn more. Okay? Thank you for bringing that up. Have a good day.